Good morning. Welcome to our second session in the Design Lives 2020 online symposium. I'm your host again this week, Professor Jennifer Drake, and I'm very happy to welcome everyone. We're going to start, as we did last week, with a land acknowledgement, and then I'll be giving introductions for our two guest speakers today. The city of Toronto takes its name from an Indigenous word, Toronto, which describes where there are trees standing in water, which I love and I think is very appropriate for the theme of our, given the theme of our sessions. Where the city of Toronto and the University of Toronto is located has been the territory of the Haudenosaunee Confederation of Six Nations, and more recently is also the territory of Treaty 13 with the Mississaugas of the Credit, who are part of the Anishinaabe Nation. Today, Toronto is still home to many Indigenous, Inuit, and Métis people, and I think it is important that we pause for a second to thank and acknowledge the people whose territory we are able to live and thrive on. More importantly, we must pledge to take our acknowledgement and turn it into action, and to be partners with them in caring for the land and water. So today we have two guest speakers. We'll bring up the slide to show the speakers that we have today. I'll just do a little bit of housekeeping to remind everyone how this platform works. We're going to pause after each speaker for Q&A, but when any professor is speaking, and if you have a questions, please post your questions into the Q&A and I will be publishing them. If you see a question that you like, please give a thumbs up so that we can moderate and make sure that we get the most relevant questions dealt with. Please feel free to ask questions on anything, whether it be the topic or something broader. We've got two guest speakers, and that will be our format for this morning. So our speakers this morning, our first speaker is going to be Professor Darko Joksimovic from Ryerson University. So Darko has been a professor at Ryerson for several years, and he has done a lot of great work with the City of Toronto and low impact development and green infrastructure. His research interests include urban water system analysis, green infrastructure monitoring and modeling, decision support and water energy nexus, and hydroinformatics. You may also have encountered Darko in the media recently with some of his work through the Flushability Lab. So there's been a lot of really exciting stuff that he's done on that, looking at the flushability of wipes and the impacts that they have on our sewer infrastructure. So I'm going to pause for a second and we're going to ask Darko to bring up his presentation. So just bear with us, it may take a minute, and invite him to talk about integrating infrastructure and the Internet of Things for living infrastructure. So good morning, Darko. Welcome. Please unmute your mic and share your screen.
Good morning. Can everyone hear me?
Yeah, you're sounding live and clear.
Thank you, Jen, for the introduction, and thank you everyone for attending. I know in this COVID era, getting up to attend a webinar at 9 a.m. may be a challenge. It is for me sometimes. Nevertheless.
We still haven't seen your screen though, just before you get going. So.
Okay, let me try that again.
Okay.
Is it good now?
Yeah, I think so.
Okay. So as Jen said, I'll talk about kind of my current thinking about Internet of Things. The DesignLIFES project is in its first year, and we're kind of starting to look at and develop concepts, and this is what's led to the current research that I'm involved in. So in terms of the outline, I'll just give a bit of history of Internet of Things and living infrastructures and how the two mesh really together. And then I'll talk a bit about the ongoing process of digital transformation of urban water management. I'm a water resources engineer, so the focus of this presentation will by necessity be on water management. And then I'll give a few ideas on the roles that I think Internet of Things can be and will be playing in living infrastructure. So if we look at the history, on the top is the Internet of Things, and if you look at literature, it's widely acknowledged that the first contribution to the Internet of Things was at Carnegie Mellon University in 1982, where graduate students and researchers didn't really want to walk down the hallway to see if there's any coke left in the machine, and therefore they wired it and connected it to the internet so that they could get an accurate assessment of the needs to walk towards that machine. And thus the Internet of Things was born. We fast forward a couple of decades, and 1999 is where the coin was officially termed in a publication, and it really meant, connected devices. 1999 is also important from the living infrastructure side of things, I think, because that's the year in which the document that arguably led to a broader adoption and awareness on low-impact development technologies. And this is the Prince George's County, Maryland Low-Impact Development Strategies document, which outlined various components of the low-impact development thinking and the whole paradigm of starting with site planning, thinking about the hydrology. And I think at that time, the ecosystem services was acknowledged as being kind of a byproduct of doing things in a low impact development way, which is something that I think has changed if we talk about living infrastructure. I should also point out that the terminology that we use is kind of all over the place. We have low impact development, green infrastructure, and so forth. And living infrastructure is kind of the latest in this evolution, I would argue, where the ecosystem services is really at the forefront, rather than some other paradigms where the shift that put the focus more on water management, urban water management, and so forth. So apparently the sound of this is not working. However, this was another breakthrough in the Internet of Things world, and I'm a bit of a technology buff, and obviously the Big Bang Theory. In 2008, they had an episode in which I presume you can't hear this, so I'll kind of give a bit of a narrative over it. The computer in the front is connected to the internet, and they're arguing back and forth about engaging it on the web. Talk that took place between basically narrates where the signal went. It went to Portugal and then to a hub somewhere in Europe, and back and so forth. And unfortunately, the sound here is Odyssey. They turned on the stereo using Internet of Things. So another seminal moment, I would argue, in that era. And now this brings us kind of to the more recent period, and this is a Eco Districts from Washington D.C. Their manual really on or living infrastructure guide. So this is where we see more kind of living infrastructure term being introduced. And obviously, in today's world, we have many interconnected devices, some of which are in our hands, like our watches, cars, TVs, washing machines. And this is a bit of a pet peeve of mine because, we're focusing all this great technology into, making our lives easier by knowing what's in our fridge, which we could open the door for. Similarly to these fellas here that are jumping around for turning on the stereo by sending the signal around the world. I think there is much better use for this technology, and this is really the question mark, is how are we going to use not these devices, but really the sensors. So, your phone has a dozen sensors, your watch may have half a dozen sensors, car has probably a couple of dozen at least. So we have all these sensors, and, we're measuring temperature and humidity, but we could do a lot more. And this is kind of the question that my current research is trying to address. Sensors and sensing is not new in the water business, in the business of urban water management. So just a couple of slides to highlight, in the drinking water sector, we really started by implementing smart meters, and the image on the left is an example of that. And the current progress of City of Cambridge, Ontario, and how they're embarking upon implementing the smart water meters. So as you can see, a third of the city is 75% completed, and they're well on the way to basically providing a full coverage of water services by installing smart water meters. Now, the picture on the right is my water bill. I took out the account number, but this is City of Toronto, where if you look here, the first reading date was 2015, January 1st, oddly, but since 2015, I've had a smart water meter, and so have the rest of residents in the City of Toronto. So Toronto is a little bit ahead on this, and basically every customer has a smart water meter. And what that means is that you can go to this little application and you can see what your water usage is and so forth. And I just noticed, being the engineer, for the first 8 days, I used 5 cubic meters, or my household did. And somehow that equates to my daily average of 170 liters, which doesn't quite make sense. Anyway, so there's a little bug in this 5 years later. But the reason I'm bringing it up is that it illustrates that, how, the most basic function or the usage of this data is to actually provide accurate billing. Water utilities and water companies rely on this as their main source of revenue. So knowing exactly how much consumer use and being able to charge for it is important. Now, if you look at this data, its reporting interval is, half a cubic meter. So this is not awfully interesting or useful if we want to drill down into actual water usage in the household. And this is where smart water meters and that area is developing into, is basically providing higher frequency and being able to use smart water meter data for a lot of things like asset management, detecting leaks, identifying, being able to detect individual water appliances use and so forth. There's a lot of research going on and a lot of practical uses of this data, but it all started from billing. In the wastewater sector, we have had both sensors and actuators being implemented in the context of real-time control, and that has evolved over the past several decades into sensors that monitor the actual water quality and then control the flows within the wastewater collection system or at a wastewater treatment plant, and both of these are well underway. In the stormwater sector, we have a couple of initiatives. The one on the left is the Santor project from Europe, which is actually kind of starting to decentralize, taking advantage of the newer technologies, decentralize the management of flows in a storm sewer network and holding them back and really diverting the flooding to where it causes the least damage. The middle slide illustrates the Opti platform, where we're using rain gauges and level sensors, sending that to the cloud along with the weather forecast, and then using that to actuate the valves and then control the outflows from a storm sewer, from a stormwater management pond, for example. And then further decentralization. This is from a couple of papers from Estonia, where they're looking at actual, adjustable plates or inlets to the system. So really, keep using the dual drainage system concept in a controllable way, and also putting in gates in the system and controlling these. So there's a great degree of decentralization being explored at the moment. And then there's a lot of other initiatives. I suggest having a look at this website. It's IWA's put a virtual journal together where there's a collection of various publications from various journals, all dealing with digital water. And this is an initiative that's, I think, less than 2 years old. Now, what are the roles for IoT in living infrastructure? I think one of the challenges that we have with green infrastructure in general and living infrastructure as well is that we need to internalize the externalities. What do I mean by that? When an environmental assessment is done that looks at alternatives for managing flows or managing stormwater, we have typically costs are involved, and then these added benefits are mentioned but not really monetized. So, for example, this is from City of Canberra's Living Infrastructure Information paper, where they rightfully say that there are a range of social, environmental, and economic benefits. And looking at large shady tree, street tree, so we're talking really simple, small-scale installation. It achieves all of this. It cleans up the air. it provides cooling, it has stormwater benefits, it provides amenity, increases property value, and provides habitat for wildlife. We know this. There are research studies that have done this on individual projects. However, if we want to really bring these in, I think that's where sensing and identifying and measuring the benefits of living infrastructure can be really beneficial. Secondly, I think we have, living infrastructure, when we look back at, for example, the real-time control of sewer systems, the first objective there was to look at the benefits in terms of reducing combined sewer overflows. And these can be readily measured, and it's not always easy, but there was it started with a single objective, right? And this is to control to minimize the volume of combined sewer overflow, for example. When we talk about living infrastructure, we do want to take advantage of the multitude of benefits that they provide. And as the previous slide said, these can range from atmospheric, stormwater. We can look at the benefits to the soil, or the changes in the soil that occur. We could look at the health of the plants by monitoring the water stress. We could be monitoring the yield in the case of urban farming. There's a variety of sensors that have been developed, for example, to look at the soil and plants in the precision agriculture. I think a lot of those are applicable and should be used in the living infrastructure context. Habitat, again, there are bee monitors out there. Images and image processing is not only good for recognizing faces and ensuring social distancing in COVID era, but we could also look at birds and rodents, and there are various ways that have already been developed and deployed to monitor how the living infrastructure could be achieving this enhanced habitat objective. Green infrastructure in general has health benefits. We're all wearing these guys, smart watches. Does being surrounded by living infrastructure lower your heartbeat? Does it have, health monitoring is a huge business and huge industry now. Can we integrate some of this external data as well into informing us and being able to quantify how the impact that living infrastructure has? Social benefits, particularly when it comes to urban farming, this is one of the big objectives that we're trying to achieve. Food security and so forth. Ecosystem services, very broad, broadly defined. So the sensors in this aspect. So I just took a couple of examples of, the pollutants found in stormwater, for example. So physical properties like pH, temperature, turbidity, these are the things that we can monitor with real-time devices. We can monitor and get online data. Some of the others like BOD, COD, nutrients, and so forth, the sensor development area is very active. So a lot of these are in the process of being developed and being tested, both in drinking water and wastewater. And I think in stormwater, we can definitely make use of more of these sensors. This is an example of related to atmospheric monitoring. This little guy costs something like $3 or $4, and it measures humidity and temperature. So the sensors scale has drilled down, the costs are going down, and the capabilities are going up. And I think we need to take advantage in measuring various processes associated with living infrastructure, so that we can take this big data, use some machine learning or artificial intelligence, and really discover how changes or how operating this infrastructure or alternate designs achieve a multitude of benefits. And that brings us back to the previous slide, that we could then monetize those and present them, and so these benefits can properly be accounted for in evaluating this as an alternative to water management, for example. And this is one of my favorite kind of newer developments. This is it's not a sensor per se, but it's a product from a company called Plant E. And what they've developed is a method to harvest energy from soil. So this is like your potato battery, right, that we did in school. But obviously it's a little more sophisticated. And they partnered with this company called Lacuna Space. And this is a company that has a small constellation of satellites that are using, that are basically picking up signals and then beaming it back down to the Earth, okay? So here they've implemented the soil-based sensor, Plant E, to a box that is transmitting signal to the satellite from solely powered by the soil itself. So this is kind of the level of sophistication that we can explore in monitoring living infrastructure. I think this is a perfect example because it doesn't rely on Wi-Fi or any local signal. Simply, you can put this anywhere. The satellite will pass over twice a day, and you can pick up this data and do it all powered by the soil. The third role I see in control is control and optimization. So I kind of alluded to this earlier, but there's a lot of work that can be done on understanding how we can actually manipulate these in real time. So we see this in water distribution networks, we see this in sewage systems and stormwater collection in general, but this whole area is just starting to be explored in the living infrastructures domain. So on the left here is a slide from a recent paper by a lab in the University of Michigan that took a bioretention area, and there's a lot of work on kind of optimizing the bioretention design. And they simply said, well, we could have different designs like free draining or one that provides internal water storage, but we could also implement a little sensor, soil moisture or a pressure sensor, and an actuated valve so that we can actually control the water levels in here. And obviously that has different implications on the biochemical processes that occur within the bioretention column. So here they were interested in how the bioretention was removing nutrients and metals, and they were measuring these in the concentration, and then trying to develop a control strategy that maximizes the benefit of bioretention, comparing it to either of the static designs, free draining or one with internal water storage, and kind of demonstrating that we could control this and actually achieve the objectives that were set out for enhanced performance of a bioretention cell. Now think about other objectives. So water, the focus here is on water quality, but obviously we could control water quantity. We could be monitoring the plant health. We could be monitoring the habitat and the soil parameters and so forth. So there's a multitude of objectives that we know we're trying to achieve, and perhaps by instrumenting this and then providing control, there are, I think, a lot of opportunities to not rely on a static design, which is something that we tend to do in stormwater management, but to actually develop and design and implement actively controlled living infrastructure. We can take some examples on this. This is some of the research that I'm doing currently with one of my master's students from the energy sector. They've realized they have a similar problem to stormwater management, where the peak demand outstrips the supply, and in our case, the peak demand is actually generated by the consumers, but not in terms of taking something from the network, but actually contributing too much to the network, right? So this is a recent paper that looked at using blockchain, or we're looking at distributed ledger technology and smart contracts, and basically machine to machine, where I love this term, distributed energy prosumer. This is not a consumer, this is a prosumer. So we could think about prosumers of our stormwater management network or stormwater collection network, and being prosumers, they might want to control some of those flows going into the network. Now, and there are papers that have looked at kind of optimally doing that on a network level, but what we're exploring is basically these smart contracts or machine-to-machine contracts that would control the inflows to the benefit of other objectives. So, for example, if you're storing the water in a bioretention cell for longer periods of time, you're going to infiltrate more, you're going to evapotranspirate more. If you're storing water in the rain barrel and in a rainwater harvesting system, that means that you can offset your demand for potable water by using that water for toilet flushing or irrigation. So these are the kind of the multidimensionality of these of the living infrastructure that we could perhaps incorporate into controlling them in a very much in a distributed level. And lastly, the role of IoT is in facilitating program management and growth. And what I mean here is that, even with LIDs and green infrastructure, there's always a concern of why would I, from the operational perspective of replacing a centralized piece of infrastructure that arguably some municipalities are struggling to maintain in good condition, and then replacing that with maybe hundreds of pieces of infrastructure scattered around the catchment. And this is a genuine concern because all these things need excuse me, need attention and management. So having a sensing network where you could, from your desktop, be alerted as to what piece of installation of infrastructure requires maintenance would be very beneficial. But from the project, from the project management perspective. Secondly, this is an example of the Ryerson urban farm, or urban farming in general, and this is obviously an advanced, I would say, piece of living infrastructure. Now, in order to, we heard from Arlene last week, this is a very labor-intensive effort. Urban farming is not, planted and leave it and then just harvested down the road. And we've heard generally in urban farming, labor is acknowledged and expertise are the two things that really are needed in order to have a successful urban farm. So by instrumenting such an installation, we could, this could basically provide a dashboard for a urban farm coordinator so that they could manage more than one facility, right? You can't have, I think, expanding or growing this program of urban farming really will not happen by having an urban farm coordinator on every roof. This is just not feasible. And therefore, we have to use these remote monitoring capabilities, if not control as well, to facilitate the growth of the program by having a coordinator being able to look after and provide their expertise and contribute to the growth of urban farming in general. Obviously, there's no shortage of challenges on the IoT side. So starting from the security, and actually one of the slides that I had earlier was from an article that pointed out to 10 largest blunders of IoT, and this involves hacking of baby monitors and smart home devices and so forth. And this is a big issue that is not resolved. Connectivity, we have we rely on large central databases as the number of data points increases into billions and trillions. There are some issues on the technology side. Compatibility and longevity, there's a variety of protocols out there, and when you talk to someone who might be interested in implementing this kind of concept, let's say a developer, they're interested in future proofing, right? They're not interested in putting something where the technology is going to die or be replaced by something else. And we're in this era of very fast technological changes. So this is a challenge. Standards are developing. And then finally, intelligent analysis and actions. And this is where a lot of research, particularly related to living infrastructure, exists. We're exploring in terms of communications and security, LoRaWAN, which is a long-range wireless access networks, connected to a backend called the Things Network. And the reason we're doing, there are several reasons, I'm not going to elaborate on it, but it's secure communication. It's extremely low powered and long range, so that we could basically capture a large number of these LoRa nodes, which are sensing nodes, to a very inexpensive gateway. And then all the programming and the back end is really taken care of as a free service by the Things Network, an organization from the Netherlands. And whatever little coding you need to do to actually visualize this data or bring it in, bring it to life, is done through very simple programming in for example, something called Node-RED flow environment, which is basically laying blocks rather than writing code and worrying about colon and semicolon and debugging and all the wonderful things that we used to do. We're also working with a company called Padlocks, and they're on the verge of providing secure Wi-Fi for to the public, so secure public Wi-Fi, and these are the two concepts in terms of the secure communication protocols. They have very different capabilities. Obviously, LoRa is not very broadband. You can, you cannot send a lot of data, whereas Padlocks and the Wi-Fi obviously gives us that broadband capability. And I just want to close with the need for this for living infrastructures. This is a picture from a map from 2014 pointing out to basements flooded due to two events. 2000, which I was here. I was actually driving through Etobicoke where the water was halfway up my my wheels. I missed the 2005 event, but in any case, there was a lot of basements that flooded from these two events. So this is an aged map. Since then, we've had a couple of more events that have generated basement flooding, and this is the current state. So basically, all of Toronto is considered a basement flooding area. It used to be, 32 or 33 areas. Now, there is the risk to at least basement flooding or the need to control the stormwater extends right across. And even though there are multi-billion-dollar projects underway to particularly dealing with the combined part of the system, we do need to implement living infrastructure across entire drainage areas, and this will not be possible, I would say, without taking benefits from the Internet of Things world, and that have the potential to achieve some of the things that I've discussed today. So that ends my presentation, and look forward to questions.
Thanks, Darko. That was really good. So I'll just remind everyone again, if you have a question, please enter it into the Q&A. And as they come in, I'll be publishing them. And if you see a question that you would really like to have addressed, please give it a thumbs up. So we already have a couple of really good questions, actually. So we'll start with this first one from Job. With a long history of SUDS or LID in the Netherlands, we find that their installation is still very problematic. And I think that's something that we see here in Canada too, that just the construction and installation, a lot of things can go wrong. So the question is, how do you foresee the robustness of an already problematic system? How do you see addressing this by making them yet even more complex by adding this adaptive or smart component?
Well, the complexity that's introduced is the challenges that I think that you outlined deal with capacity and expertise for proper construction is one thing, and then probably maintenance challenges. I mean, I've heard examples where the Parks Department goes in with a lawnmower to maintain a bioretention area, right? These are, I mean, both in construction and in landscaping and maintenance, I think there is role for IoT to be played. But in terms of increasing complexity, monitoring for example, of a rain garden can simply be done by inserting or measuring the levels in the thing, right? So the added complexity can be very minimal. So just providing kind of a wet well and using an ultrasonic sensor connected to a LoRa node that can be readily replaced. These things are extremely cheap. I mean, such a device would cost $20–30 perhaps.
So I guess I'm going to just, before we move on to the next questions, or building on that, then if these the infrastructure is increasingly readily available and cost effective, why aren't we doing it? What are the barriers that you sort of see that are why aren't we hooking up all of our infrastructure and making it smart or adaptive and connecting it so that we collect data and that we also manage it in real time?
Well, I think we haven't caught up to the IoT world and the miniaturization and the lowering of cost and of sensors. One of the things that we're doing on a current project is actually doing conventional monitoring. And when you go out to a supplier to buy monitoring equipment, you're looking at thousands of dollars, right? This is not feasible if you want to put this in every rain garden in the city, right? So we're looking down to the equipment that costs, in the order of tens of dollars. Obviously, you're not going to get probably the same accuracy. You may, what about battery life? What about maintenance? How long does the sensor last, and so forth. So this is where I think that the research is needed, and that we're doing is looking at really low-cost devices that could be implemented in broadly. So right now, I think is over-reliance on conventional monitoring solutions that are quite expensive. Right?
Yeah.
They may be reliable, they may be accurate, but they're not going to be implemented across the board.
Yeah. Okay, so our next question comes from Sylvie, and again, they're very good questions, but they're long. Yeah. So engineers are very risk adverse and always adding large safety factors. I imagine a safety factor with IoT would be having the operating system without internet. With stormwater, we have distributed systems and no one really notices. So it could be off or broken before someone notices. So what are the ideas that you might have for safety factors for stormwater systems in particular?
Well, the safety factor is built into the design. So there are two issues here. One is monitoring, and I would add, that would actually add to the safety factor of the design. Because if you're capable of getting a text message if your bioretention is clogged, I think that's a good feature to have. If you're talking about control, all these devices have a fail-safe and a safe-fail modes that basically operate in a static mode if the electronics go awry or communication is not received, or there's simply a bug in the program, right? So there's from the other fields, again, from the field of industrial engineering, from aerospace. I mean, I remember reading a paper 20 odd years ago where Rolls-Royce was receiving data from their engines as the plane is flying and doing the diagnostics real time. So we're talking, we think this is complicated, and these are complex systems, which they are because they interface with people and the environment and so forth. But if you look at look at SpaceX landing the bloody thing on the needle. There are vastly more complex electromechanical systems where sensors and sensor management has been really employed for decades.
So just as a follow-up, though, I'm curious, with the transition to reliance on sensors, and yes, like being able to have an alert, when something is off would be fantastic. Doesn't this also create the opportunity to actually create new risks where we're too reliant on this? The example that comes to mind is in Hamilton, one of their overflow systems had a gate, and it was instrumented, and there was a sensor that was supposed to be detecting, I guess, the water depth, and the sensor wasn't it wasn't accurate enough, and so it didn't actually trigger, and so the gate was left open for 4 years, releasing billions of combined sewage flow over that time to an already degraded water system. So how can we as engineers, what do we need to do so that we embed in these more smart systems that kind of redundancy and factors of safety?
Well, first, I think the stakes are lower. I mean, if you're talking about a rain garden versus a $10,000 cubic meter CSO tank that's leaking. But nevertheless, the stakes may be lower, but the complexity of the system is smaller. And in fact, if things go awry, you're notified, right? And this is where the data analytics comes into play, right? So you could deploy, and this is the challenge that water companies encountered when they started putting sensors in their networks. All of a sudden, the operator sees 1,200 alarms a day. What do I do with this, right? Or security may be an issue. If you're controlling someone's rainwater harvesting system, you don't want someone tapping into it and flooding the thing, right? There are challenges, but as I pointed, the IoT field has developed over the years, right? And even though there are some challenges, we're talking about kind of low stakes environment here and the capability of addressing these concerns at this small, inexpensive level. So, if a sensor doesn't work, and it costs $30, it's just a matter of someone, going and popping and putting a new one in. You know, these things can be very simple.
Yeah. Okay, so I think we've got one last question. So this is from Sean Thomas. Demonstration projects that show the utility of the approach seem critical. What do you see as the lowest hanging fruits for smart sensors and IoT systems in living infrastructure?
The lowest hanging fruit is, well, you know, using the cheapest sensor and the most robust sensor. So I think temperature and humidity is something that, I mean, as I said, the sensors costs are trivial and they are becoming more robust. Next to that, I would put level sensing. I think ultrasonic and you know, pressure transducers. There's a variety of sensors that we could be that are also inexpensive, quite robust. And as I said earlier, all we need to do is put a wet well or perforated pipe in our installation and put a wireless level sensor that doesn't actually have to be hugely accurate, but it tells you if, you know, that along with rain information, if your bioretention or whatever device is filling and emptying, that's good, it's working, right? And over long term, you could actually tell how well it's performing. And if it's clogged or, you know, things go awry, it's a lot easier to generate a reliable alarm than from a water distribution network where your pressures and flow have huge oscillations and variations and so forth. These are, you know, more predictable and less complex devices that could be readily monitored. So we should be putting these in every installation that goes in.
So I've got, for last question before we move on to our next speaker is, you know, with my research group and my experiences, over design of green infrastructure seems to be pretty pervasive. I can't, you know, can't list the number of times we've gone to a site and it's supposed to be on tight soils and we're expecting to see lots of water and nothing's coming out because we're already just embedding so much over design. Do you see this as, you know, that practice as being like a barrier for preventing the uptake of IoT because it's going to be difficult to demonstrate the utility or the benefit because of the way we currently design our infrastructure? Or do you think those benefits would be apparent if we just put the sensors in?
Well, the challenge I think that we have, and I've observed this as well, is that, you know, this over design, you know, often when you're doing a pilot project and you're trying to demonstrate the utility of something, you don't want it to fail, right? So you know, you kind of build up a little on those safety factors. And that leaves a lot of room for optimization, right? So if you could, I mean, we're still learning how these things actually operate, as you say, in tight soils and so forth. But we could be learning at a lot faster rate, right? And if, yes, it's over designed, but we'll know, you know, how much it's over designed, and then the next installation may be smaller and utilizing data to reduce the cost, to you know, increase the robustness and reliability of these installations. So I recognize it's a challenge, but I think IoT could actually help towards addressing it.
Okay, thank you so much, Darko. This has been really interesting, and I think some excellent questions from the audience. So thank you to everyone watching as well. So